geopolymer concrete with industrial waste products. Okay. So I am Dr. Shyamal Gucchait, the Assistant Professor in Civil Engineering Department of NIT-Rourkela. Okay. So the first slide. Ah, so this is the first slides. Actually, this is about contents, what I will be discussing. It will actually having some contents like introduction, then the process and mechanism of geopolymer concrete, advantage, disadvantage, and what are the present research work, what we are doing here in NIT Rourkela. And after that, we'll be discussing the result analysis, conclusion, those things. Okay, so first I'll start with introduction. Now, in introduction, first I'll discuss about the sustainability. Sustainability means that what is actually everlasting. Okay. So in for our case, for civil engineering, sustainability is related to the sustainable development. Okay. And in sustainable development, we have three things. First is the environmental protection. Okay. So first is the environmental protection and enhancement. The next is the social progress, and third is the economic development. So if we talk about sustainable development, we have to consider all these three. We have to consider the environmental protection, the social development, and the economic development as well as. Okay. So now if we talk about the environmental sustainability, we can have different kind of terms like environmental sustainability related to the renewable energy, if we can produce the renewable energy source, wastewater treatment, then the behavioral change in daily life, some ecological restoration, or waste recycling and reuse, use of green transport, okay, sustainable industrialization. Uh, for our case, for this topic, we'll be most focusing on the waste recycling and reuse. Okay, because we'll be developing the geopolymer concrete with the waste products from industry. Now, before coming to the geopolymer concrete, first I'll discuss about this that ordinary Portland cement (OPC). What is that OPC? I think you must know these terms. OPC. OPC is the ordinary Portland cement. So it is used for the normal concrete. Okay. To produce the concrete, we use this OPC, ordinary Portland cement. And this material, it is very consumed. I mean, the concrete is the most consumed material after the water. Okay. And it is also the most energy intensive material. Okay. Because to manufacture all the basic materials to prepare the concrete, it requires heavy energy. Okay, so that's why it is the most energy intensive material. Next is that it cost very means high carbon dioxide emission. Means if we produce the concrete, all the raw materials used in concrete, that creates heavy carbon dioxide production in the environment. Okay, we can approximately say that 1 ton of cement produces approximately 1 ton of carbon dioxide. Okay, so these are the two reference. Actually, it is not 1 ton. It may be 0.9 or 0.8 ton. So approximately it is 1 ton of carbon dioxide. Okay. Next is that so we are talking about the environmental sustainability. That means we are in the first slide I have shown you that we will be using the waste material, different type of waste to produce the geopolymer concrete. So in this slide you can see the different type of industrial waste which we can use, industrial or waste from the different sources. So type of waste. Now from type of waste can be broadly classified into three types: industrial waste, construction and demolition waste, and third is the agricultural waste. In industrial waste, we can have different type of ash like coal fly ash from the coal industry, GGBS or GBFS means you can see at the below that GGBS means ground granulated blast furnace slag, or we can call it as a ground granulated blast furnace slag. So GGBS or GGBFS. And the second GBFS, it is also a slag, all the slag actually it is came from, or we can collect from the steel industry. It is the byproduct of the steel industry. Okay, so GBFS, it is the granulated blast furnace slag. Next is silica fume, or we can have the recycled plastic waste. Okay, so different kind of industrial waste we can collect and use in concrete. Next is the construction and demolition waste. So we can again means reuse the construction waste like recycle coarse aggregate or recycle fine aggregate in place of natural coarse aggregate and natural fine aggregate. Okay. And the next is the agricultural waste. Agricultural waste means we can use different kind of waste from the agricultural sector like oil palm shell, coconut shell, rice husk. So for different means for the replacement of different materials like rice husk, we can use as a replacement of binder. Oil palm shell and coconut shell, if we can take it and you can make it in a perfect shape, so in place of natural coarse aggregate, we can use oil palm shell or coconut shell, or even in place of natural fine aggregate. But before to that, we have to crush those kind of shell. Okay, to take it in perfectly means size. Okay, for the replacement. Next, so now after we discuss the normal concrete with ordinary Portland cement, okay, and after the discussion of the different kind of wastes from the industry or the agricultural sector, or from the construction and demolition waste, we can move forward to geopolymer concrete. Okay, so this term, this geopolymer, it is first actually this geopolymer concrete, it is a cementless concrete. Here we will not be using the cement as a binder. Okay, so the binder will be alternate to cement. And this geopolymer concrete is first developed by the Joseph Davidovich. He is the French scientist, and it is developed in 1978. So what is the geopolymer concrete? Actually, it is the inorganic polymer, okay, manufactured by the alkali activation of the industrial waste with the alkali activated solution. Okay. So basically it is a inorganic polymers, and it is generated by the alkali activated solution. We'll be discussing in detail how to develop the geopolymer concrete with alkali activation. Okay, this is the process. Next thing is that this is very environmental friendly. Why? Because we are using the different waste product like fly ash, GGBS, okay, uh, as a component material to prepare the geopolymer concrete. And this geopolymer concrete, the materials, the ingredient should be means it should be high content of silica. It should contain high content of silica. Okay. Geopolymer concrete reduces the carbon dioxide emission by 80%. And we can have the reference, you can see. So if we produce the geopolymer concrete in place of concrete, the carbon dioxide emissions will be reduced to approximately 80%. It may be more or less, approximately 80%. Now, coming to the process and mechanism. So process is what? Process to prepare the geopolymer concrete is like that. So silica and aluminum atoms in the source material means the fly ash, GGBS or silica fume. So these are the source material. So the silica and aluminum atoms present in the source material, it will be dissolved by the alkaline solution. So we will be providing some alkaline solution, and in which this silica and aluminum atom will be dissolved, okay, ionized by the OH ions, and a gel will be prepared. So that gel, it is called the geopolymer gel. Okay, and in that process we have to do the heat curing or temperature curing normally. So to produce the geopolymer concrete, generally we applied the heat curing or temperature curing, but in now recently we can means the geopolymer concrete nowadays it is prepared with ambient curing also, means normal way in temperature. Okay, normal temperature condition. Now this geopolymer gel, it will then binds the aggregates and the unreacted source materials to form the geopolymer concrete. So first of all, what it is means doing here means silica and aluminum atoms in the source materials, it is dissolved with the alkaline solution to form a gel, and that gel actually it acts like a binder, and it binds the aggregate and the unreacted source materials to form the geopolymer concrete. So geopolymer basically it is an inorganic gel or inorganic polymer, you can say. Now, in this slide, you can see the mixing procedure of the industrial waste based GPC. GPC means the geopolymer concrete. So to prepare the geopolymer concrete, how to mix the different industrial waste. Okay. So first what we'll do a dry mix. Dry mix of fine aggregate, coarse aggregate and binders. Binders means here the fly source materials, fly ash or GGBS, those things. Okay. So we'll first dry mix for 3 to 5 minutes. Then we will prepare a solution of NaOH and Na2SI3. Okay, prepared for 24 hours prior to the mixing. So prior to the mixing of all these, means mixing of the solution and the this dry mix, we have to prepare this solution 24 hours prior. Okay, and after this solution prepared in a pan mixture, we have to add some extra water and super plasticizer. Okay, as per the mix design. Then we will mix all this, means this fine aggregate, coarse aggregate and binders, this dry mix, and as well as this solution, NOH and Na2SiO3 solution, and we'll wet mix for 3 to 5 minutes. So that will prepare the geopolymer concrete. Okay. So basically here first we'll be doing the dry mix for the binders and fine aggregate on coarse aggregate, and simultaneously or 24 hours before we will prepare a solution of NOH and Na2SiO3. Then we'll mix all these and we'll add water and super plasticizer as per the mix design to prepare a wet mix. Okay, we'll do the wet mix for 3 to 5 minutes, and then in that process we'll prepare the geopolymer concrete. So this slide, you can see the different kind of ingredients utilized for the geopolymer concrete. So first of all, the source materials, that is the fly ash and GGBS, you can already we know. And this source material, we to select the source material, we have some criteria. Like it should be amorphous, that means it should be reactive. Okay, if any material it is amorphous in nature, it will be reactive. Low water demand, and it should be effective and easily available. Okay, it should have lower particle size. So this is the main criteria of the selecting the source materials. After that, the source material and alkali activators. What is alkali activators? Actually, it is the solution of NaOH or KOH with the Na2SiO3, that is the sodium silicate. So this is the alkali activators. So source material like fly ash or GGBS plus alkali activators plus aggregates, it forms the geopolymer. So you can see here the fly ash in the figure, fly ash or GGBS or a combination of fly ash and GGBS. Okay, so this is the binders, then the sodium silicate solution plus NaOH pellet. Okay, these two will with these two we can prepare the solution. Okay, the alkali activated solution we can prepare with sodium silicate and sodium hydroxide pellet. And another next thing is the aggregate. Okay, natural NFA means natural fine aggregate and NCA means natural coarse aggregate. Okay, here actually you can see the full form. All the means the full form of the short terms it is mentioned means in the bottom. You can see here in the slide. Okay, so combining all these three, then that means the binder plus the alkali activated solution plus the coarse aggregate and fine aggregate, the geopolymers is prepared or geopolymer concrete is prepared. So this is the complete process. Mechanism actually, I have already told you that this dissolution of silica and aluminum atoms actually takes place through the OH ions. Okay, and it forms different polymeric structure. So this polymeric structure actually we can call it as a polysialate. Okay, and this sialate stand for the silicon oxoaluminate building unit, a single building unit, polysialates. So these chains and rings formed and cross links through this bridge, silica aluminum bridge through the OH ions. You can see in this figure, this is the compounds of geopolymer. So these three, you can see in this figure, these are the three monomers of the geopolymer concrete. The first is that silica, when the silica and aluminum that element, the ratio is 1:1, then we can have this polysialate. One means you can see here that one ALO4, that molecule is combined with the one SiO4. Here O means the OH ions. Okay. So here silica and aluminum ratio is 1:1. So this is first monomer, polysialate. The second monomer is when the silica and aluminum ratio is 2:1. Okay, so that is called sialate siloxo. You can see here also the molecular structure. Okay, so 2 SiO4 and 1 AlO4. Okay, so this is called the sialate siloxo, second kind of monomer. And the third kind of monomer is when there is 3 SiO4 and 1 AlO4. Oh, that means when Si is to Al ratio is 3:1. Okay, so that is called the sialate diluxo. Three kind of monomers it means actually develops when the geopolymerization process happens. And in the table also you can see the effect of different kind of sialates when the first one, okay, that is the sialate. So when Si and Al is to ratio is 1:1, so that material it is good for the fire protection. Then the polysialate siloxo, when the Si is to Al ratio is 2:1, so that monomer it is good for generating the cementitious property and it enhances the strength. Okay, and the third monomer, that is the sialate diluxo, when the Si is to Al ratio it is 3:1. This monomer it is good for the thermal insulation of the concrete. Okay, so now you can see in the figure also, so different kind of monomers. You can see three types of monomer we can have, one, two, three types of. After that, what happens? Some gelatinization process happens and then restructuring of these monomers. After that, the polymerization happens and this is the final product. This is the geopolymer we can have, or it is prepared, okay, due to the reactions of alkali activated solution and the source materials. So this is the final product after the polymerization. Now, in this slide, in slide 14, you can see the production of the geopolymer concrete or matrices under alkaline or acidic medium. Now, means till now we have discussed the production of the geopolymer concrete in alkaline medium with alkaline solution. See in the right hand side, you can see the production of the geopolymers with the alkaline solution. Okay, and the final product is alkali aluminosilicate geopolymer. Similar process we can have in the acidic medium also. Okay, and so for the acidic medium, you can see the hydrogen ions, the presence of the hydrogen ions, and for the alkaline medium, this red actually red that marks it indicates the hydroxide ion, OH ions. Okay, so in the acidic medium, the compound product is silico aluminophosphate geopolymer. Okay, so similar process, that means the geopolymer concrete with geopolymerization, that process can happen in alkaline medium or acidic medium. The product will be different kind of polymer, geopolymer. Okay, so either of two we can choose. Generally, the traditional one is the use of alkaline medium. That means alkali activated solution. Use of sodium hydroxide or potassium hydroxide along with sodium silicate solution. So that is the traditional process to produce the geopolymer concrete. So that means the traditional geopolymer, it is the alkali aluminosilicate geopolymer. Now, what are the advantages? Advantages is that it is a cutting world's carbon, means carbon oxide emission, that it will be reduced, better compressive strength. Then it is having the property of cold resistance and heat. It create the less heat like the normal OPC concrete. Okay, it is having the low permeability, eco-friendly, and the next advantage is that the low creep and sinkage value. So the geopolymer concrete, the creep and sinkage strain, it will be less. Okay, creep means the sustainable development, strain development. Okay, due to the strain developed due to the sustainable stress, so that will be also less. Okay, and sinkage will also be less. And the most important thing that we are converting the waste product into some useful products. Useful products means that is the concrete. Okay. And we are having some disadvantages also if we prepare geopolymer concrete. So that means the geopolymer concrete have some disadvantages, like difficult to create because it is requires a special handling process. Okay, difficult to create because some reaction process are there, so we have to control those reaction process. Next is the premix only, means because of this difficulty for creating geopolymer. So generally means we can the geopolymer concrete is available or sold as a precast or the premixed material. Okay, so that is also a disadvantage. The next is the geopolymerization process is very much sensitive. Okay, so first of all, it is very much means we have to control the procedure. Otherwise, it will be very difficult. Okay, so uniformity has to be achieved. If we could not perform or could not reach the uniformity in producing the geopolymerization, then it will be difficult. Okay, so that means a standard practice should be followed. Okay. Now, till now we have discussed that what is the normal traditional concrete using the OPC, means ordinary Portland cement. And after that we have discussed the geopolymer, what is geopolymer and what is geopolymer concrete. Okay. Production of the geopolymer concrete, what are the ingredients are there. Okay. So after that, now we'll be discussing means in our NIT-Rourkela research means in the lab, structural lab, one of my PhD students in means doing the research on geopolymer concrete, and what he is doing in place of natural fine aggregate, he is using GBFS. Okay, granulated blast furnace slag sand. Okay, as an replacement of the natural fine aggregate, because nowadays concrete is very means due to the means to produce the concrete. Means that consumption of concrete is so high that there is a scarcity of natural fine aggregate. So we need the replacement. In our lab, we are alternatively means we are means mixing or as a replacement of natural fine aggregate, we are using GBFS, granulated blast furnace slag sand. You can see the figure here. Okay. The other you can see in the left side the cement and fly ash and GGBS. These are the binder. Okay. So in geopolymer concrete, in place of cement, the fly ash and GGBS, it is the binder. Okay. So in place of cement, we are using fly ash and GGBS. In place of natural fine aggregate, we are using GBFS. And in place of natural coarse aggregate, to make it a lightweight concrete, we can use different kind of lightweight coarse aggregate, like lightweight air-cooled blast furnace slag. Okay, we are trying to introduce these as a coarse aggregate, such that the geopolymer concrete prepared would be lightweight also. Now, this slide is all about material and experimental detail. Okay, what the means what are the tests requires to uh, means find out the characteristics of the materials, and then the different kind of testing. Say first we have to do the collection of the materials, then we have to perform the physical and chemical testing of the materials. After that, we can prepare the mix design. Okay, then after that, mixing and casting of the materials, and then after that we'll be performing different kind of mechanical test. Okay, like compressive strength, flexural strength, split tensile strength, and durability properties. Then we can collect the results. So you can see in the material characterization, the first thing it is we are characterizing the fly ash and GGBS. Okay, in fly ash you can see the specific gravity, it is 2.19, and GGBS it is 2.83. So GGBS is the weight is high compared to the fly ash. Okay, and you can see the test methods. You can see in the table the codal provision. Okay, so according to this codal provision IS 4031, we are performing the test, and you can see the fineness also. GGBS is much more fine. The unit is centimeter square per gram. So if GGBS is more fine, so that means the reaction ability of GGBS is much more high compared to fly ash. Okay, but GGBS is much more costly compared to fly ash. If you do the cost comparison, then you will find that GGBS is costly compared to fly ash. So we have to use the mix of things. Means here to prepare the geopolymer concrete, we are using the FA, the fly ash and GGBS as a 50-50 ratio. Okay, such that we can have the once the cost is less and as well as we are getting sufficient strength. Next is the physical properties for NFA means the natural fine aggregate and GBFS means the alternate sand, that granulated blast furnace slag sand. Okay. So you can see here the appearance, the natural fine aggregate, it is the brown. Okay. Natural fine aggregate, this is the brown, and GBFS you can see the greenish gray. Okay, gray kind of color, and the loose bulk density and the compact bulk density you can notice here. So the bulk density of NFA, it is high. So that means it is heavier. Natural fine aggregate, it is heavier. And GBFS, it is lighter. So if we prepare the geopolymer concrete with GBFS, it will be lighter. Okay. Specific gravity also you can see it is less. Means NFA it is high and GBFS it is less. Water absorption, it is almost the same. And we both this fine aggregate, it is following the grading zone 2. Fineness modulus is also very close. Okay. And this picture you can see in the slide 21. See, this is the particle size distribution graph, means the graph actually. So that means here you can see that the minimum means here 100% sand is there, 0% GBFS. Okay. Then we are increasing the GBFS content, 25%. Sorry, minimum and maximum, it is the upper limit and the lower limit uh, we can have from the code, IS code. Okay. And this 0%, 25%, 50%, 75%, 100% means we are 0% GBFS means 100% sand. 25% GBFS means 75% sand and 25% GBFS. So like that way, you are increasing the GBFS content and reducing the sand content. And all for all the mixes. So this graph is in between these two minimum and maximum range. Okay. So it is provide, I mean, following the particle size distribution graph from the codal provision. Okay. Whatever we are using. Now this is the X-ray diffraction, XRD patterns from the X means we have performed the XRD of different kind of materials, so say fly ash, GGBS, NFA, GBFS. Why we are doing this? To find out the different molecular compounds, means what are molecules are present in those materials. Okay, so you can see here different kind of Q means the quartz, M means the mullite, H means the hematite. Okay, so those kind of atoms are present, not atom, compound is present. So we can perform this kind of XRD analysis to find out the what are the compounds are there, okay, in that material. This is another kind of microstructural characterization, that is the X-ray fluorescence or XRF. From the XRF also we can find out the different oxide compounds in the material. Okay, so the yellow color, it is representing the different oxide presence of the oxide compound in GBFS. Red it is GGBS and FA is the fly ash. So you can see from this graph that calcium oxide, it is high for the GGBS. Okay. Then for the silica, actually silica oxide, it is high for the fly ash. Okay. And in GGBS also you can see, means the GBFS, the sand also, in that sand also silica content is much more high. Okay. So we can have those kind of means XRF study also, okay, to find out the oxide position, oxide means percentage. Now this is also a microstructural characterization. One way of microstructural characterization, that is the scanning electron microscope, SCM analysis. You can see the SCM analysis of fly ash. The shape of the molecules here, the circular, rounded shape. For the GGBS, actually, it is a flaky kind of shape. And GBFS, it is means actually random kind of shape. Okay. So you can find out the molecular structures also for different kind of material with a scanning electron microscope. Okay. And if you take these pictures and perform the next thing, that is the energy dispersion spectroscopy, EDS analysis from the SCM images, then you can find also the elemental composition, like the the presence of the atoms. Okay, like oxygen, aluminum, silica, ferrous means the Fe actually. So you can see for the fly ash, the Al percentage is 13.8. Okay, and silica it is 20.2. But for the GGBS, that is the alternate of the sand, so that is having the silica percentage 10, and the calcium percentage is 15, aluminum percentage 21. For the GBFS, sorry, GGBS, it is the powder, and GBFS, that is the sand. You can see the silica percentage is high compared to GGBS, and calcium percentage it is less compared to GGBS. So you can find out the atomic composition from this energy dispersion spectroscopy, EDS analysis. Now after that we have already means we can perform different kind of test and find out the different property like the phase property, workability property, strength properties, compressive strength or flexural strength, then shrinkage properties. And after that we can find out other things also like thermal behavior and means different kind of durability test like chloride permeability, acid resistance, sulfate resistance. Okay. So other durability tests are also there. We can find out one by one. Okay. And to find out the fresh and mechanical properties of the geopolymer concrete, we have to prepare some kind of say cube or cylinder like that. For workability, we have to prepare the first term of a cone. For compressive strength, we have to prepare the cubes. For split tensile strength, we have to prepare the cylinder. For flexural strength, we have to prepare the prism. The size also it is mentioned here. You can see the cube is 100, 100, 100 millimeter. Okay. And for the cylinder, the diameter is 100 and height is 200. And for the prism or the beam, that is for the flexural state, it is 100 into 100 into 500. We are following AIS or ASTM code alternatively. And will be performing the curing the 7 days, 28 days, 56 days, and 90 days. Okay. So after different days, we can find out the strength. So this is the casting images for the cube, cylinders, and the prism. Okay, this is the cone, you can say, for the workability test. And uh, these are the cubes for the compressive strength. So we can find out. And this is the slam value we can see. After the slam value means workability test, we have find out for the different composition, and we have find out the maximum slam value. It is coming for the uh, concrete which is having 100% sand. Okay. After that, if we add that GBFS, the alternate sand, the workability it is reducing. Okay. And when the sand it is 100%, then the workability is high. Approximately more or less same, but when we are adding much more GBFS alternate of sand, what is happening here? The pores it is filling. Okay, so workability it is reducing. Then this is the test results for the compressive strength. In the compressive strength, we can have 7 days, 28 days, 56 and 90 days properties here like that. And you can see for the different combination OPC G0 S100 means the sand 100 and the GBFS sand is 0 quantity. Then GBFS 25 sand 75, GBFS 50 sand 50, GBFS 75 sand 25, GBFS 100 and sand 0. So these are the combinations, mixed combinations. And you can see the compressive strength for different combinations. And from this graph, you can see the maximum strength we are getting. Either it is 7 days or 28 days or 56 days. Maximum strength we are getting for this combination. G50, S50. So that means sand 50 and GBFS sand 50. So that is the optimum combination we can have for the from the compressive test result. Okay. Similarly, we have performed the split tensile strength. Okay, by performing means on the split tensile strength on the cylinder. Okay, diametrically opposite, will apply the load and find out the split tensile strength using the standard formula. Okay. Here also we can see that the same kind of mix we have developed and we have done the split tensile strength of those kind of mixes. And for G50, S50, we are getting the highest strength. Okay. So split tensile strength. Value it is like 1.5 to 4.5 or 5 approximately. Okay. For the compressive strength, you can see the value. It is actually our target that FCK. Okay, the mix design it is done for M35. So our the target strength it is approximately 45 like that. So we are getting more than that. Approximately more than that means at 28 days. Okay. So for say S50, G50, S50 in 28 days, we are getting approximately 45, 46 like that. So this is the test, flexural strength test. Flexural strength test, how can do it? We can do it by applying the 2-point test on the prism or a beam. Okay, flexural load, applying the flexural load, and we can find out the strength. Okay, here also the range is 2 to 4.5 or 5 like that. And for G50 S50 combination, we are getting the maximum flexural strength. And flexural strength test also we have done for 3 different curing periods: 7 days, 28 days, and 56 days. So this is the 3D representation of the strength. You can see for the compressive strength, for the flexural strength, and for the split tensile strength. For the compressive strength, you can have the different means designation. The different means designation I have already told you. And in the y-axis, you can have the compressive strength. And in the z-axis, we are having the ambient curing period. Okay, so there is 3 axes. Means designation, x-axis, y-axis compressive strength, and z-axis is the ambient curing. Okay, so you can see that after certain stage, after 28 days, you can say the strength is more or less same. Means it is not increasing very high rate. Okay, it is actually approximately same. Similar trends we can have for the flexural strength as well as for the split tensile strength also. Okay. So different combinations we can try and we can plot in 3D and check what are the relation between those means variations or variables. So next is that does means we have already done that compressive strength test or different kind of durability test and the that fresh property, that is the workability test. So now we have to confirm that why the strength is developing. Okay, to do that we have to do the microstructural characteristics of the specimens, of those specimens. Here you can see in this figure. So this is the microstructural characteristics, the scanning electron SCM images after 28 days, and you can see for the different combination. G0 S100 means SAN 100, GBFS SAN 0. So then after that G25 S75, G50 S50, G100 S0. And you can see that for normal concrete, that the that CSH, the calcium silicate hydrate, it is the main reason for the stain development. Okay, that molecule. But for the geopolymer concrete, actually the stain develops due to this CSH and the Nash formation, CNASH formation. Okay, so CAS and Nash, if it means if it produces at high content, then that means that the strength is developed. Okay, or the strength is developing high. So you can see that for the G50 and S50, we are having much more means CAS and Nash formation. Okay, so because of that reason, we are getting the high strength. Okay, and from this ACM plot also we can find out the ITZ region. Okay, means that is the ITZ zone. Okay, we can also uh, find out. Okay, so that is the zone for weaker region, weaker strength actually. Okay. And here also you can see the means the 56 days and 90 days means that figure. Okay, and here the final product we can have, that we are having actually CNSH, and CNSH is the final thing we are having. Because of this, we are getting the high strength for the geopolymer concrete. For normal concrete, it is the CSH only, calcium silicate hydrate. But for geopolymer, it is the CASH and NAS, calcium silicate aluminate hydrate and sodium silicate aluminate hydrate. Okay. Now, what are these possible applications of the geopolymer? So in construction and repair of highway, because the strength development in geopolymer, it means the rate is very high compared to the normal concrete. So for the repair and maintenance, we can use the geopolymer. Okay. Road and airport runway or pre-stage bridge, we can use. Okay. Because of it high resistance to acid attack, we can use in very acidic environment. Where the acidic environment is there, so in that case, in place of normal concrete, we can use the geopolymer concrete, like sewer pipes or landfills. Okay. or due to higher temperature resistance, geopolymer concrete can be used in chimneys or fireplaces. Okay, it is suitable for long life and stability in those conditions, very high temperature condition. Geopolymer concrete can also be, it is a very highly resistant to chloride formation. So we can use in the coastal areas, means for offshore structure, we can use geopolymer concrete. Okay. Hello. Is it okay? Can you hear me?
Yes, sir. Yes, sir. Yeah.
Yeah. So
Yeah.
after that, we can use it is in cold climate places also. Okay. So there are a lot of applications because it is durable and it is getting very high strength in very less curing days compared to normal concrete. We can use it is as a for the repair work as well as for the means different environment. Okay. Different environment, means toxic environment, like where the acidic nature is there, or very means chloride means chloride environment it is there. Okay, means there is a chance of the chloride corrosion. Okay, or corrosion of the reinforcement due to the chloride ions. Okay, so in those cases also you can use the geopolymer concrete. Now see here, the University of Queensland Global Change Institute, it is actually, they have built the world's first building with the geopolymer concrete. Okay. So this is the use of the geopolymer concrete. Now, after that preparation of the geopolymer concrete, nowadays actually scientists are looking forward for different kind of geopolymer concrete. Okay, let's say one of the special kind of geopolymer concrete is the lightweight geopolymer concrete. We also in the lab we are trying to prepare the lightweight geopolymer concrete. Okay, so lightweight geopolymer concrete is what? When we are using or preparing the geopolymer concrete with alternate aggregates such that it is lightweight. So that means it will be lighter compared to the conventional concrete. Okay, if we prepare the lightweight geopolymer concrete, what the advantage it will have? It will be very, it can easily handle, we can easily handle that concrete and transport from one place to another during the construction. So the cost of the transport it will be less. Okay, and the lightweight aggregate material we have to use for preparing the lightweight geopolymer concrete is like oil palm shell, sintered fly ash aggregate, or lightweight expanded aggregates. So lightweight blast furnace slag. Here we are using, like I already told you, that we have used the lightweight blast furnace slag or lightweight blast furnace air cooled slag. So in place of natural coarse aggregate, if we use this kind of aggregates, we can prepare the lightweight geopolymer concrete. Okay, in the lab, we have used the lightweight blast furnace air cooled slag and we have prepared the lightweight geopolymer concrete. But the problem is we are facing here, you can see the figure here it is provided, the lightweight that air cooled blast furnace slag, it is porous in nature. Okay, so the if we use this kind of coarse aggregate, the density it will be less, specific gravity it will be less, so that such that that means actually the weight will be less, but the problem will be it is porous. So that means the strength you will be getting less. Okay, so that's why, because of that reason only, see here the combination C100. So this is the density we are getting. Density, as we are increasing, the L means here lightweight aggregate. So as L is increasing from 0 to 25, 50, 75, 100, the density it is decreasing. Okay, say for normal, when we are using the normal coarse aggregate, the density was about 2500 kg per meter cube. But after that, it is reducing. But the strength we are the slump also we are getting less. Okay, and you can see the compressive strength also it is coming less. So that means that when you will be using the lightweight aggregate, the strength will be less. So research is going on. We have to use some kind of fiber or some kind of other thing to control the strength and to get the higher strength. Okay, so we have to make a balance here, balance between the density and the strength. Okay. So use for future development. So we can use, means we can do different kind of research in geopolymer concrete in future. Okay, making the fiber reinforced geopolymer concrete or replacement of fine aggregate with different kind of waste material. Okay, fiber reinforced geopolymer concrete or lightweight geopolymer concrete we can develop. Okay, so these are the research trend, you can say, or future research trend we can do, or we can perform the research in geopolymer concrete. Okay. So concluded remarks, I have already told you that Compared to the OPC, it is having very high early strength. It is having low creep and sinkage value. It is having the fire resistance property. Okay, so all advantage are there, but the disadvantage is that we have to control the thing. In laboratory setup to prepare the geopolymer concrete, it is okay, but in real life condition or in actual site condition, uh, we have to means the preparation of geopolymer concrete means to prepare the geopolymer concrete, we need that control. Okay, if we can controlly prepare the geopolymer concrete, then it will be a good option, alternative option for the normal conventional concrete. Okay, so that is the use we can have for geopolymer concrete. So with this sentence, I'll conclude here. So, and if you have any question, you can ask.
Yes, sir.
Yeah, yeah.
Hello.
Uh,
Yeah. So this geopolymer concrete, you said that
mm,
cement, it is completely replaced by
mm,
fly ash and GGBS,
mm.
100% replacement.
Yeah, it is 100% replacement. So actually, it is the
Uh,
cementless concrete. Means alternative to
okay.
cement, the fly ash and GGBS. It is also a binding material. It is having some pozzolanic property, binding nature. Okay,
Yeah, but we had
and
done this because I am from environmental stream. So we had done
uh,
this GGBS, this concrete, but we up to 60% replacement we did, and we
okay.
tested for the in the sewage treatment plant units. It
Mm.
is more, I mean, applicable. It is there in the sewage treatment plant
With
and effluent.
normal, see, we can use as a replacement of cement also that FA or GGBS, but
Yeah, up
the
to 60%
geopolymer
we
that,
did
yeah, it is okay, but for geopolymer
because the
concrete
strength
we
was
can
reducing. If you completely replace, the strength was reducing.
no. Actually, for the geopolymer process, this is different. It is not like the CSI gel formation. I have told you already in the first few slides that we have to do it in a different way. We have to provide the alkaline solution also, NaOH and Na2SiO3 solution also. Okay, so that will react with the FA and GGBS and prepare the geopolymer. If we do it like that way, then
Mm.
we achieve the strength.
Then
Otherwise,
completely
with
replace,
normal you can completely replace. Otherwise, with
completely replace
normal
by
thing, we
100%.
cannot do.
Normal
Yeah,
thing, yeah,
you can
normal
do
thing
that.
up to 60% only it was that. And it
Yeah,
was
yeah,
more
yeah.
efficient in sewage treatment plants. So we had tested
Hmm.
for that. Sewage treatment
For
plant units are there, no?
yeah,
Sewage
yeah,
treatment
yeah,
plant and effluent treatment plant in industries.
yeah.
So it proved to
It
be
is more
more
durable.
beneficial there. Yeah, more durable there.
Hmm. Hmm.
So that is with that first procedure, if you do that, then it is 100% replacement,
Then a
you
hundred
mean?
percent replacement. Yeah, yeah.
Okay. Otherwise, conventional, it is only up to 60%.
Up to 50, 60, whatever you achieve in the lab,
Or
you can do it.
60%, yeah. We did that.
Yeah.
Yeah.
Yes.
Sir, I
Thank you,
have a
sir.
question.
Yeah.
Uh, uh, Usually concrete, if you are mixing on site, we can have some kind of a rotary machine where we mix the dry mix and water and mix it.
Hmm. Hmm.
So if you want to use geopolymer for construction,
Hmm.
so do we need to have a specialized equipment like for mixing
No
that
specialized
NaOH?
equipment. In the normal thing, see the Na2SiO3 and NaOH solution that you have to mix. Okay, that before the dry mixing. Okay, man, before when you want to construct this geopolymer concrete, before one day you mix that solution, you prepare that solution. Okay, and in the next day, what you will do it first, you will do the dry mix of the fine aggregate, coarse aggregate and with that FA and GGBS, that binder. Okay. Then you will dry mix for 3 to 5 minutes. After that, you will add that liquid solution, NOH and NTSO3, that solution to that. And after that, you will mix in the normal pan mixer. Okay. And you will prepare the
Mhm.
geopolymer concrete. It is a normal standard thing you can do.
And is there any study on the flowability, like if you are pumping to
Flowability,
like
all these things are there. See, means nowadays that the researcher is trying to develop the matlab self-consolidated geopolymer concrete. Okay, means increasing the
Mhm,
flowability. Actually,
mhm,
see in that figure that workability is reducing because the pores it is thing. So you can add the special kind of that is plasticizer, super plasticizers. Okay,
mhm,
to make it more
mhm,
flowable actually.
mhm, mhm, mhm. One more question.
So.
Uh,
mm,
you said that the geopolymer has better resistance to
Hmm.
corrosion.
Hmm.
What exactly could be the reason? Like
Corrosion means
what can
actually actually to confirm that we have to perform different kind of durability testing. Okay, but that chlorine,
Yeah, but
see,
excuse me, sir. Yeah, actually, it is more resistant to corrosion. We had that testing on the sewage treatment plant,
yeah,
this
yeah,
units, no? So we subjected
because
it to
see,
that
it is actually the
this
slag
chloride and that, the wastewater.
where
So it was more
the
durable.
answer is yeah, more
Though I
durable
don't know the
because the
answer, but it was more durable.
slag, no, because the slag we are using more, no. So because of that reason, it is more durable. In likewise that pozzolanic slag, the chloride
Mm.
reaction and those things, okay, that will
Mhm.
reduced when you use the in place of OPC, if you use the pozzolanic slag cement, means the
Mhm.
PPC or PSC, the durability increases. Okay, because of the same kind of reason, as we are using the fly ash and GGBs in very high proportion, so that's why the durability issues are reducing. Okay.
So
So
that NaOH solution, and you said no adding that by that
Hmm.
process. What
It
is
is
that
also
percent?
the alkaline in nature. Okay, so alkaline nature is
How you
also
have come in?
helping.
What is that percentage you're adding, and how is that? How much that solution?
That NO is an Na2SiO3. So that you'll
NaOH.
do that you have to do the mix design. Okay, otherwise because
Okay.
different kind of combination it is there. No, so that you have to do the mix.
Mm.
You can find out in